So example 7 from your book says, how large an n does each type of approximating sum require to approximate this integral with an error guaranteed to be less than 0.0001? And I will just note here in the homework exercises, you're going to see they'll give you an error of plus or minus 0.0001. We don't have to worry about doing anything different for the positive or the negative. It's just saying you can be above by this much or below by this much, and we throw in the absolute values, and that takes care of that anyway. You want to use the K1 and K2 constant values that we already figured out from the last example because this is the same function. All right, so in this situation, n is an unknown. So let's begin with the left approximation formula. Now, I want n to be my unknown here. And I want this error to be less than or equal to 0.0001. Again, you can ignore the plus minus. All right, so I'm going to go ahead and now substitute into the formula the things I do know. Now to solve this inequality, first of all, I want to clean up the left side as much as I can. So once you have this inequality, we know that n has to be a number bigger than or equal to 1. It's a number of rectangles. You know, it's got to be 1, 2, 3, 4. It's not going to be negative. It's not going to be a decimal. In other words, I know it's positive. So what I can do at this point is multiply this entire inequality by 2n. Now, if n could take on negative values, that would actually flip my inequality sign. But I'm safe here. I know that n's positive, so I can do this. On the left, the two n's are going to cancel, and you're going to be left with 1.284. On the right, you multiply 2n times this decimal, and you're going to have 0.0002 with an n. And then we can finish getting n by itself by dividing both sides by the decimal. And I get 6,420 is less than or equal to n, or for those of you who prefer your variable on the left, n has to be at least as big as 6,420. I need a stinking lot of rectangles in order to ensure this kind of accuracy if I wanted to use a left approximation. So probably I don't. Okay, so again, this is telling me I would need at least 6,420 subintervals. Now, for comparison, the book, again, because they used a different K1 value, they used 1.5, they actually got 7,500. Again, you needed even more because your K value wasn't the tightest K value it could be. All right, so the rest of these are going to work the same way. So I'm going to do the setup, and then I'm going to kind of skip through the calculations. So the next one that I'll do is I will calculate for a midpoint. I write the error bound formula, and I say I don't want it to be any more than this quantity. So now I'm going to substitute and do the calculations the same way that we did above. Just make sure you use K2 this time. And I'm going to pick up this calculation here at this step. We're still going to divide off that coefficient from the n, but again, we got an n squared this time, so let's talk about what that does to the calculations. This gives me the number 950 2.08 and some other stuff. And I'm going to keep that number on my calculator because the last thing I need to do is take a square root. To get n by itself, I need to take the square root of this gigantic decimal on my calculator to get the most accurate answer I can, which I got 30 point, we'll say 856. So what this is telling us is that if you use a midpoint approximation, you need at least, I would say, 31 subintervals. So wow, right? What a dramatic difference between a left approximation and a midpoint approximation. That's significantly fewer and is, obviously going to make calculations much easier. Finally, you would do the trapezoid calculation the same way. I forgot to mention, but remember that because the right approximation uses the same formula as the left, the answer for the number of subintervals you would need would be the same for the right approximation. So we either have to use 6,420, or if we do a midpoint approximation, we can use 31. Now, since midpoint is usually the best, that's probably the lowest number of subintervals, but we'll go through the trapezoid and see what that turns out to be. And as we expected, for the trapezoid, I ended up that the number of subintervals needed would have to be at least 44. So that's the truly powerful version of the error bound theorem is, like I said, generally speaking, if you're doing real world applications, you have some idea of an acceptable level of error. And then this tells you what number of subintervals to use for a given approximation to guarantee that you're not going to exceed that error. Okay, pretty cool.